Alright, let's continue on with data types. Every value in Rust is of a certain data type, which tells, it's like kind of like the objects in Python, if you know Python, which tells Rust what kind of data is being specified, so it knows how to work with that data. We'll look at two data type subsets, scalar and compound. Keep in mind that Rust is a statically typed language, statically and strongly typed, which means that it must know the types of all variables at compile time. The compiler can usually infer what type we want based on the value and how we use it. Interesting. In cases when many types are possible, such as when we convert a string to a numeric type using parse in the guessing game section, we must add a type annotation like this. Let guess a colon there, and then a type, assignment operator, something parse, expect not a number. So this is changing the string into a number, U32. If we don't add the U32 type annotation shown in the preceding code, Rust will display the following error, which means the compiler needs more information from us to know which type we want to use. Consider giving guess an explicit type. Type annotations needed. Okay. You'll see different type annotations for other data types. Scalar types. A scalar type represents a single value. Rust has four primary scalar types: integers, floating point numbers, booleans, and characters. You may recognize these from other programming languages. Let's jump into how they work in Rust. Integer types. An integer is a number without a fractional component. We used one integer type in chapter 2, the U32 type. This type declaration indicates that the value it's associated with should be an unsigned integer. Signed integer types start with an I instead of U. So if this was I32, that would be a signed integer, meaning you have negatives as well as positives, and unsigned meaning only positives. That takes up 32 bits of space. Table 3-1 shows the built-in integer types in Rust. We can use any of these variants to declare a type from an integer value. Alright, so we got these. What the heck is that? Arch. Alright, these are pretty large numbers. 128-bit. 128-bit. Is that 2 to the power of 28? Wait, let me check something. 32, that's 4 million. Alright, 4 billion, sorry. 2 to the 16 is 65k. Okay, so that's a very large number. Each variant can be either signed or unsigned and has an explicit size. Signed and unsigned refer to whether it's possible for the number to be negative. In other words, whether the number needs to have a sign with it, or whether it will only ever be positive, and can therefore be represented without a sign, unsigned. It's like writing numbers on a paper. When the sign matters, a number is shown with a plus sign or a minus sign. However, when it's safe to assume the number is positive, it's shown with no sign. Signed numbers are stored using 2's complement. I'm not going to click on this. It's a way to represent signed numbers, basically. Binary representation here. You can read about it on Wikipedia, 2's complement. Each signed variant can store numbers from that to that, -1, inclusive. So if it's 8 bits, for instance, you got from negative 128 to positive 127, basically, the signed version. The unsigned version goes from 0 to 255. So unsigned versions of these can store twice as many plain numbers as the signed versions because you lose one bit to the sign itself. Okay, so an I8 can store numbers from that to that, which includes, okay, that's exactly what I calculated. Unsigned variants can store numbers from that to that, yep. Additionally, the I-size and U-size types depend on the architecture of the computer your program is running on, which is denoted in the table as arch. 64 bits if you're on a 64-bit architecture. Oh, so that's architecture. I see. And 32 bits if you're on a 32-bit architecture. I wonder if there is an advantage to using the same bit integers as your architecture. I doubt it, but, well, I don't know. You can write integer literals in any of the forms shown in table 3-2. Note that number literals that can be multiplied, numeric types, allow a type suffix such as 57U8. Interesting. You can do underscore and the 8222 maybe? Yeah. Number literals can also use underscore as a visual separator to make number easier to read. Okay, decimal, and then you got the hex, octal, binary, and byte. I have not learned how to read hexadecimal, or binary for that matter. So how do you know which type of integer to use? If you're unsure, Rust defaults are generally good places to start. Integer types default to I32. The primary situation in which you'd use I-size or U-size is when indexing some sort of collection. Why? Let's say you have a variable of type U8 that can hold values between 0 and 255. If you try to change the variable to a value outside that range, such as 256, integer overflow will occur, which can result in one of two behaviors. When you're compiling in debug mode, Rust includes checks for integer overflow that cause your program to panic at runtime if this behavior occurs. Okay, Rust uses the term panicking when a program exits with an error. We'll discuss panics in more depth in the unrecoverable errors with panic section chapter 9. So these are like exceptions in Python and just errors, in general, which cause your program to stop. When you're compiling in release mode with the release flag, Rust does not include checks for integer overflow that cause panics. Instead, if overflow occurs, Rust performs choose complement wrapping. Really? In short, values greater than the maximum value the type can hold wrap around to the minimum of the values the type can hold. Okay, this is sometimes seen in games and whatnot. Okay, I see. The program won't panic, but the variable will have a value that probably isn't what you were expecting it to have. Relying on integer overflows wrapping behavior is considered an error. You bet. Okay, I think this is good. This is also in line with Rust's philosophy of just giving errors in your face, I think, because you will, or your users will probably notice this, and you can fix it. To explicitly handle the possibility of overflow, you can use these families of methods provided by the standard library for primitive numeric types. Wrap in all modes with the wrapping method, such as wrapping add. What do you mean? What does that mean? Return the none value if there's overflow with the checked methods. Return the value and a boolean indicating whether there was overflow with the overflowing methods. Okay, saturate at the values minimum or maximum values with the saturating methods. I have no idea what those mean. Floating point types, but these are probably good practices to use if you're worried about integer overflow. Rust also has two primitive types for floating point numbers, which are numbers with decimal points. Rust's floating point types are F32 and F64, which are 32 bits and 64 bits in size respectively. The default type is F64 because on modern CPUs it's roughly the same speed as F32, but is capable of more precision. All floating point types are signed. Here's an example that shows floating point numbers in action. Okay, let x 2.0, that's F64, that's the default, is it? Yeah. But if you explicitly give it the type F32, it becomes F32, of course. The F32 type is a single precision float, and F64 has double precision. Okay, fine, if you say so. Numeric operations. Rust supports the basic mathematical operations you'd expect from all the number types: addition, subtraction, multiplication, division, and remainder. Integer division truncates towards 0 to the nearest integer. The following code shows how you'd use each numeric operation in a let statement. All right, so integer division truncates towards 0 to the nearest integer. Okay. Let's sum that difference. Okay, product quotient truncated results in -1. Sure. Remainder is, that's going to be 3. Each expression in these statements uses a mathematical operator and evaluates to a single value, which is then bound to a variable. Appendix B contains a list of all operators that Rust provides. Not going to look at that right now. Boolean type. As in most other programming languages, a Boolean type in Rust has two possible values, true and false. Booleans are 1 byte in size. The Boolean type in Rust is specified using bool. For example, let t true, let f bool false. You don't actually need to do this, I guess. I mean, I think implicit is fine in this case. You don't need to do explicit type annotation because true and false can only be bool types, right? Right? The main way to use Boolean values is through conditionals, such as an if expression. We'll cover how if expressions work in Rust in the control flow section. Okay, character type. Rust character type is the language's most primitive alphabetic type. Here are some examples of declaring character values. Let's see Z. Okay, let's see character. What is that? That's not an uppercase C, is it? I want to know what that is. Yeah, that's not, I don't think that's an uppercase C. That's a different character. Heart-eyed cat. There we go. Sure. Note that we specify character literals with single quotes as opposed to string literals, which use double quotes. Okay, this is an important distinction that Python doesn't have. I come from Python, so it's important for me. Rust char type is 4 bytes in size. 4 bytes, that's 4 Unicode scalar value, which means it can represent a lot more than just ASCII. obviously, 4 bytes. Yeah. Accented letters, Chinese, Japanese, and Korean characters, emoji. 0 with spaces are all valid char values in Rust. Unicode scalar values, USV. I don't think I've seen this mentioned before anywhere. Range from U that to U that, and U this to U this other thing, inclusive. I have no idea what the heck this means. However, a character isn't really a concept in Unicode. So your human intuition for what a character is may not match up with what a char is in Rust. We'll discuss this topic in detail in storing UTF-8 encoded text with strings. I know UTF-8. I've never seen this concept. Compound types. Compound types can group multiple values into one type. Has two primitive compound types, tuples and arrays. Okay, so they're collections. Maybe they have something else that's called collections. Okay. Sequences. The tuple type. Compound types. Okay, so tuples or tuples and arrays. Tuple tuple type. A tuple is a general way of grouping together a number of values with a variety of types into one compound type. Tuples have a fixed length. Once declared, they cannot grow or shrink in size. Okay, so fixed length arrays. We create a tuple or a tuple by writing a comma-separated list of values inside parentheses. Each position in the tuple has a type, and the types of the different values in the tuple don't have to be the same. We've added optional type annotations in this example. Let tup and the types and the values. Hello. All right, let me just type that. I'm bored without typing anything for a while now. Tup I32 F64 U8 assignment operator, and then we got the values. 500 for I32, 6.4 for F64, and 1 for U8, unsigned 8-bit integer. Don't forget the semicolon. Variable tup binds to the entire tuple because a tuple is considered a single compound element. To get the individual values of a tuple, we can use pattern matching to destructure a tuple value like this. Really? Okay, so this is called unpacking in Python. Let's do that. Let x get the value of 500, y get the value of 6.4, and z get the value of 1 by using assignment to the tuple or tuple, whatever you want to call it. And then println. Let me just copy this. There we go. Value of y is whatever. Cargo run. Don't like it. Unused variable z. Did I type something wrong? Oh, it's just warning me. These are not used. The value of y is 6.4. Okay, so I didn't use the x and z values. That's why the compiler is warning. These are not errors, just warnings. Okay. Program first creates a tuple and binds it to the variable tup. It then uses a pattern with let. Take tup and turn it into 3 separate variables. It's called this destructuring because it breaks the single tuple into 3 parts. Finally, the program prints the value of y, which is 6.4. We can also ask, why do different programming languages call the same thing different names? I wonder. Copyright reasons or something? I mean, what if we run out of words in English to call things things? What then? Anyway, we can also access a tuple element directly by using a period, followed by the index of the value we want to access. For example, oh, okay, I see. You don't use square brackets, you use period. Let me try that. Hello. Okay, I got all of these, but I'm not printing any one of those. I'm gonna get warned again. So let me print those. 500 and the other one and the other one. 6.4 and 1. Let's cargo run. Not found in the scope. What do you mean, man? Okay, this should have been top. I'm going to change the x's to top. There we go. Now what? All right, I got the values, 500, 6.4, and 1. There we go. Okay, so the zero index element of the tuple can be accessed by doing period 0. The 1 index element, period 1. The 2 index element, period 2. So 0 index element, 1 index element, 2 index element, in case you're not familiar with the indexing thing. This program creates a tuple x and then accesses each element of the tuple using their respective indices. As with most programming languages, the first index in the tuple is 0. With most C family languages, let's say, the tuple without any values has a special name, unit. Really? Why, oh why? This value and its corresponding type are both written okay, and represent an empty value or an empty return type. Okay, so you can specify an empty tuple like this. But tuples cannot be changed, so where does it make sense to declare an empty tuple, I wonder? Expressions implicitly return the unit value if they don't return any other value. Oh, this is the null type, none type, something like that. They use it as a none type. Interesting. So void functions would return this, maybe. The array type. Another way to have a collection of multiple values is with an array. Unlike a tuple, every element of an array must have the same type. Unlike arrays in some other languages, arrays in Rust have a fixed length. It's not dynamic. And tuples are also fixed length, I think. Tuples also have fixed length. Arrays also have fixed length. We just love fixed length. We write the values in an array as a comma-separated list inside square brackets. Okay, so this is more familiar to me as a Python programmer-ish person, let's say. Arrays are useful when you want your data allocated on the stack rather than the heap. We'll discuss the stack and the heap more in chapter 4, or when you want to ensure you always have a fixed number of elements. An array isn't as flexible as a vector type. Okay, there is a vector type. A vector is a similar collection type provided by the standard library that is allowed to grow or shrink in size. Okay, so vector is what I think of when I think of a list in Python, for instance. If you're unsure whether to use an array or a vector, chances you should use a vector. Chapter 8 discusses vectors in more detail. All right, I believe you. However, arrays are more useful when you know the number of elements will not need to change. For example, if you were using the names of the month in a program, you would probably use an array rather than a vector because you know it will always contain 12 elements. Okay, you write an array's type using square brackets with the type of each element, a semicolon, and then the number of elements in the array like so. Okay, like this. So an array cannot contain a mixed type. So they all have to be of the same type. Do they? You can also initialize an array to contain the same value for each element by specifying the initial value, followed by a semicolon, like this. Okay, and then the length of the array in square brackets. So 5 elements inside the array, which all have the value of 3. The array named A will contain 5 elements that will all be set to the value of 3 initially. This is the same as writing let A that, but in a more concise way. Okay. Accessing our array elements. Okay, you access them differently than you access tuple elements. Interesting. An array is a single chunk of memory of a known fixed size that can be allocated on the stack. You can access elements of an array using indexing like this. Okay, so you use square brackets and the index inside the square brackets, which is what you do in most C family languages, maybe all, I don't know. In this example, the variable named first will get value 1 because that is the value at index 0 in the array. So that's index 0 element, index 1 element, index 2 element, etc. Second we get, invalid array element access. Let's see what happens if you try to access an element of an array that is past the end of the array. Index out of bounds error. Panicked, index out of bounds. Yeah, of course. This is standard in C family languages. All right, let's write the code then. Let A be an array of these guys. And then what? Print a line. Please enter an array index. I command thee. Let mute index string new and we need a standard input output there. Standard IO. Okay, and then IO standard input, and then we got a read line, and mute index, and then expect. I expect you to fail. Failed to read line. That is the expectation at least. Okay, I guess these guys should have some indentation there. Let index usize. What is this? This is typecasting, isn't it? Usize index. We're not parsing it though. Why are we not parsing it? Oh, we're parsing it down here. Right, trim and parse and if error index entered was not a number. Okay, so we got index from the user, read it from the standard input, and then we typecast it into usize, which is architecture dependent. Was it? Let's see. Yeah, unsigned architecture dependent integer, whatever your architecture is, minus 64-bit. And then we're getting let element a index, creating another variable for that, and then printing it. Print ln is the value of the element at index is element is element. There we go. I think this is it. Anyway. And let's compile it. Cargo run. Expected that or this. What do you mean? Why? Use. Okay. Forgot the use keyword. Let's do that again. No method named except. Of course. Except. From Python. Expect. Let's do it again. There we go. Enter an array index 2. The value of the element at index 2 is 3. Thank you. This code compiles successfully. If you run this code using cargo run and enter, the program will print out the corresponding value at that index in the array. If you instead enter a number past the end of the array, such as 10, you'll see the output like this. Let's try that. Cargo run. 10. Out of bounds. There we go. The len is 5, but the index is 10. Great feedback there, actually. It telling me the length. The program resulted in a runtime error at the point of using an invalid value in indexing operation. The program exited with an error message and didn't execute the final print line statement. When you attempt to access an element using indexing, Rust will check that the index you specified is less than the array length, which is very smart. I wonder why other programming languages, or compilers rather, don't do that. If the index is greater than or equal to the length, Rust will panic. This check has to happen at runtime, especially in this case, because the compiler can't possibly know what value user will enter, of course. This is an example of Rust's memory safety principles in action. In many low-level languages, this kind of check is not done. And when you provide an incorrect index, invalid memory can be accessed. Yep. I think C is guilty of this. I don't know about C++. Rust protects you against this kind of error by immediately exiting instead of allowing the memory access and continuing. So C is therefore not, well, this is not about typing, but C is not a strongly typed language. It's statically typed, but not strongly typed. Rust, on the other hand, is like the anti-C in most respects, but very much like it as well, like the twin brother. Chapter 9 discusses more of Rust error handling and how you can write readable, safe code that neither panics nor allows invalid memory access. All right, cool. So this part of me learning Rust is done. Yes, I'll see you guys in the next part.